Besides the issue of scale, organisms can change over time. For example, young individuals may group together to form a school or herd or something like that for protection. But then as they get older, they're able to manage out on their own. There may be social interaction as well. For example, in elephants. An elephant herd is a group of females. The older females have plenty of experience that they can teach to the young elephants where to find the food and water and stuff like that. And then you've got your young elephants there. But when a young male elephant gets old enough, he'll go out on his own, and then we'll try to find a herd of females when it comes time for reproduction. But otherwise, he's off by himself while the females and young stay together. Another example here. Pine trees. Well, seeds scatter fairly randomly. Yeah, they'll tend to be a little closer to the parent plant than way off somewhere, but a lot of pines do have a little flap on the seed, kind of similar to a maple seed, allowing it to flutter in the wind and blow a ways. So they're going to be spread out kind of randomly at the start, or maybe a little clump closer to the parent plant. However, one got a little better spot, grows a bit faster. It's shading its neighbors, and they're not going to do as well. So over time, ones growing too close together will tend to die off, and we'll be left with a more dispersed pattern for our older trees. Kind of like what sometimes done in gardening. Plant lots and lots of seeds, and then you go through and thin. Decide which are the plants that are not doing so well. Pull up those, make more room for the ones that did grow better. As opposed to just planting a few seeds and hope they all will make it. Well, depends on your seed quality. They might not, but if you plant a whole bunch, okay, you got a little more growing than you needed, but well, then you thin them out, make it more dispersed. Population size, again, no surprise how many babies, how many are dying, those will affect our population size. But as I mentioned already, dispersal. How many move out of an area, how many move in. The balance between those will also affect how big our population is. All sorts of factors, no surprise, are going to affect these. Age for beginning to reproduce. If individuals wait longer before reproducing, well, they're going to have less time to make lots of babies. You're likely to see a somewhat lower growth rate if individuals not reproduce until they're relatively old. Once they start, how long? What proportion of the lifespan is dedicated to reproducing? How often? Most organisms, there's a particular season or other distinctive time when there is reproduction, and then not at other times. This is obviously not true of humans, but a number of species do have that pattern. How many babies at a time? How long do you live? How often are individuals dying? All these are important. You'll get different patterns over time. So, if you have a population and there's plenty of food, plenty of all the resources needed, then you tend to have an exponential population growth because there's plenty available, but we only start out with a couple of individuals. Even, say, 2 oysters, there's a limit to how many babies they can have. It's probably a few million, but still, there's a limit. Okay, you get some of those surviving. Now, instead of 2 oysters, we've got, say, 10 oysters. They're going to be able to make 5 times as many babies as 2. So on up. And so once our population gets big enough, then it can have a lot of babies. And so you can see this happening. But you can't just keep on going up. There's going to be a limit for any real population. And so this is going to slow down, maybe stop, maybe even lead to a decline if things got too many before they responded to the limits. So in real world, our population may start to grow fast, but eventually it's going to have to level off. And this carrying capacity is symbolized by K. I haven't checked why they use K instead of C. It may have been from another language, or just they were using C for something else. Now, of course, environments actually change. So the capacity is going to change some with that. But we can think of there being some limit. There's going to be a limit to how many individuals of a species can be in a place at the same time. So, okay, it starts out looking exponential, but then levels off. And so you get this kind of S-shaped logistic population growth pattern. However, sometimes instead of leveling off there, things shoot up, and then, we got too many, they can't survive, then you get a crash. And so it's more up and down. Human population growth has tended to follow the exponential pattern of late. Now, a lot of this relates to the scientific advances that we've had that enable us to do more. For example, advances in medicine. We've got some dips related to major disease outbreaks and the like. Also, agriculture, being able to grow a lot more food, getting better crops, and growing in new places, things like that. But the growth is slowing. There's a limit. There's only so many people that can be supported by the resources on Earth. So we do need to think about what is a fair and just way to try to have an appropriate limit to the human population. Obviously, there are plenty of very bad options for trying to limit the population by killing a bunch of folks. We need to think more carefully about what will be good ways of trying to maintain a balance. What is the limit on how many people can live on Earth? Estimates range quite widely. We are seeing a decline in birth rates as well as death rates. Death rate has declined faster, so we tend to get more people as a result of that. But, okay, how many people can live on Earth? Well, what do you call living? What standard of living are you assuming? What amount of resources being used? What sort of new technology may come along to allow us to be more efficient? How much waste are we making? Things like that. A lifestyle fairly typical for Western countries in the US uses a lot of resources, much more than typical in many other parts of the world. Using more resources is going to require fewer people. But we have major economic development happening in many parts of the world, most dramatically in China and India. But globally, most parts of the world have been seeing some degree of progress in standards of living. But then, say they get movies or TV and see what is portrayed as lifestyles in the US or Europe, something like that, and they want that. And that's going to take more resources. So there's definitely challenges to think about what is an appropriate level of standard of living, resource use, things like that. What affects population size? We can think of both density dependent and density independent. You may recall we had a little bit of this back with evolution as well. If population density affects how much environmental factor influences the population, it's density dependent. This is all too familiar today. Social distancing. We're trying to decrease the population density, spread folks out, which makes it harder for the virus to spread. Loads of people all crammed into a small space, it's easy for diseases to spread. So that is an obvious density dependent factor. Predation, competition. These are also typically density dependent. Predators. Hey, there's a whole bunch of yummy deer living here. Great. We're going to focus on hunting deer. Oh, what about the one loose cow I saw in the woods? That's one cow. Trying to focus on chasing that, that's not going to get us very far. Okay, so obviously predators are not usually conversing like that, but that basic source strategy. There's a lot of something. I'm going to focus on eating those, not really bother looking for something that's hard to find. Similarly, competition. Well, the more other individuals around you, the more competition there is. So all of these then tend to have bigger effects on our population the more dense our population gets. And so this will tend to give a negative feedback pattern. Negative feedback means when something happens more, something else tends to kick in to make it happen less again. So again, our example, say we get lots and lots of individuals in an area. This is great for our parasites and pathogens, and so lots of individuals getting sick and dying, our population crashes back down. Now there's fewer individuals and much less spread of disease and parasites, so the population builds back up and we get this back and forth negative feedback due to the density dependent pattern. Competition, interaction between two individuals that are trying to use the same resource. Maybe it's space, food, sunlight, water, any resource that two individuals both want, and they can't both make use of the same stuff at the same time. So the more one individual uses of the resource, less for everybody else. This can be competition with others of the same species or between species. Then we have the density independent factors, something that will affect the population no matter what. Most commonly abiotic, because biotic things are going to be influenced by the populations of other things they interact with. For example, extreme temperature, a very cold winter, stuff that can't live in those temperatures is going to die. Doesn't matter if there were a lot of them or a few, they're all going to die. If you go to places like a lot of Alaska, northern Canada, there are lots of mosquitoes in the summertime. Quite a problem. But adult mosquitoes cannot live in an Arctic winter. They all die. It's going to be only eggs and larval stages that are able to survive through the winter. Doesn't matter if there were only a few mosquitoes or a lot of them, they die. It's too cold for them. Another pattern in organisms is the reproductive cycle. Do you have one big effort right at the end of a lifespan, which is similarity, or are individuals able to reproduce multiple times through their lifespan? We have a number of insects where the adult stage basically is only focused on finding mates and reproducing. They may eat a little bit, or maybe not any at all in some cases. And so that is a simiparous pattern. The larval stage has spent its time largely eating, building up energy reserves. Now the adult uses them for reproduction. Other invertebrates, a lot of the squid and octopus are simiparous. They only reproduce right at the end of the lifespan and then die. Among other things, means that even though they're pretty intelligent, learning can't be passed on the way it can for humans and many other mammals. Some other things, number of fish, plants. For example, salmon, heading up the river to spawn. Most salmon then, once they spawn, die. One time at the end of lifespan. Agave, plant example, spends several years building up energy from its photosynthesis, storing that away, and then at the end of lifespan, it will grow its flower stalk, make a bunch of seeds, and then the plant dies. And there are various others. This is a challenge, for example, in panda conservation. Pandas eat bamboo. Bamboo tends to be simiparous. So it grows for a long time, and then all the bamboo in one area flowers and dies. All the bamboo died, what does the panda eat? Well, if it's got someplace else it can go to, it can go eat the bamboo over there that's on a different cycle. If it's stuck in just one little area that's the only preserve left, and all the bamboo there dies, that panda's awful hungry. So these do affect not just the biology of that organism, but of others as well.